So am I live, Vicky? Not yet.
Yes, you are. Take it away. You can start the
Okay.
presentation.
Okay. Hi. Let me share the screen with the my presentation. My first. Okay. I hope everybody can see the first slide. So I'm Gustavo, and I work at Linaro as a software engineer, focused on TVM, running on microcontrollers. Thanks a lot for joining. The idea of that presentation is first to share the updates about microTVM, and also talk after that about TVMC, which is a command line interface tool for TVM, specifically in the context of microcontrollers. So first of all, I just would like to give a bit of context about TVM for those not so much familiar with Apache TVM. So Apache TVM is a compiler framework for compiling deep learning models for various targets and device architecture. And this is basically allows you to run, to get a deep learning model and run it in a optimum way. So in native code on a target device of your interest. So TVM allows to compile code for targets like CPUs, GPUs, NPUs, so it can offload an operator to run on which is part of a model to run on a neural processor unit. It also can generate code to run on browsers. So it generates codes to WebAssembly, for instance. It can compile a model down to bit stream, so it can the model can be flashed into a FPGA, and it also runs on microcontrollers. So TVM is not really used to train train or design a neural network, for instance. This is done usually using a different tool, and then once your model is trained, TVM will automatically generate and optimize the tensor operators for your model for running on a specified target of your interest, hopefully in a quite optimized way. So this is very so running your model will be much faster in that sense. And TVM also accepts a bunch of different formats for your model. And so it accepts formats exported from Keras, PyTorch, TensorFlow, TensorFlow-Lite, and so on. So in summing it up, the goal of TVM is to close the gap between productivity-focused deep learning frameworks and the performance-efficient focused hardware backends. Okay, so in that picture, I just would like to, this is a very high-level view of the TVM architecture with the main layers composing it. And on the upper layer, you can see the front end, which will be responsible to parse and to import the models in different formats, as I've mentioned on the previous slide. And in the middle, we have of course, it is about the compiling chain of which, so there are a couple of intermediate representations down to LLVM, for instance, low-level LLVM code, so a code that LLVM can understand. So in that sense, the LLVM library is heavily used by TVM. So so LLVM library will generate the source code for the operators necessary to execute your model on a given target. And after that, once you have the source for the operators, you can use it. Usually, you are going the TVM will use a Keras compiler which runs on the host to generate the final native code which will run on the device. Okay, so another interesting thing in that picture is the box on the upper right corner, which says automatic optimization. So it means that it is actually picturing the fact that TVM allows one to tune the operators automatically to run on a given device. And since that task is time consuming, TVM allows one to use a device fleet. So a bunch of devices attached to the TVM host will be used to find the optimum settings for a operator in a target to run the model. So this is a quite interesting feature where one can use device fleet to speed up tuning the model operators for a target architecture or device. Okay, so as we mentioned, that TVM runs on a various different hardware platforms, and it also supports. It also runs on microcontrollers, and the microcontrollers, as everybody knows, are usually quite resource constrained devices. Hence, TVM has a specific runtime, which is more lightweight, so to speak. For instance, there is a simplified version for the RPC server implemented specifically to run on microcontrollers. And to that part of subcomponent of TVM, we give the name of microTVM. So all the code necessary to run TVM on the resource constrained devices on microcontrollers, we give the name of microTVM. And the microTVM runtime has actually two types of executors. The first one, which was firstly introduced to microTVM, is the host-driven, which means that the host will drive the execution of the model. So we'll transfer the data to the device where the model will run, and we'll also drive the operator execution on the device side via a usually a serial line. So the host will drive the device in the host-driven case. And there's also the AUT-driven executor on microTVM, which means that in that case, the host is not driving the execution of a model. So if you have that kind of runtime, the AUT-driven, as soon as you power up your device, the model will start executing, and it is so not necessary an assistance from the host. And the difference between these two runtimes is that since the host-driven has got a thin RPC server, so a lightweight RPC server to communicate with the host. So usually the image flashed to the device is bigger in the case one is using the host-driven executor in comparison to the AOT-driven executor. And this is also, the execution is also a little bit slower because there is a communication involved between the host and the target device via usually a serial line. So, however, the host-driven executor is used for the auto-tuning I've mentioned when TVM is trying to tweak the knobs for the operators in a given architecture to best run the operator on the target device. So, and this is necessary, that communication with the host is necessary because the host needs to, for instance, collect information about the time spent running a given operator, which is part of the model. So it's necessary that communication between the host and the target device. So these are the trade-offs between the host-driven and the AOT-driven runtimes on microTVM. Okay, microTVM can also, it's not strictly necessary, but usually we run microTVM on top of platforms, and those platforms can be like RTOSes, like Zephyr, or or Arduino, for instance. So that's what we mean by platforms on a microTVM world. Okay, so now that we know where microTVM fits in TVM, I would go for speaking about what is new since, and by new I mean the last 4 or 5 months, so roughly since my last presentation on the first Linaro Connect this year. So for Zephyr platform, there are new boards around which microTVM is supported on. So there is the MPS board, which is a standard board provided by ARM, which contains a Cortex M33 CPU. There's also the NRF 5340 decay board, which contains also from Nordic, which contains also a Cortex M33 CPU. There is the Zinc MP from Xilinx, which has a Cortex R5 core, and also there are some additions regarding the additional support we got to RISC-V CPUs for 32 and 64 bits. Okay, this is what is new on Zephyr platform, and there is also a recent contribution from Octomel for supporting Arduino on microTVM. So in that case, Arduino brings boards which are based on ARM32 and ESP32 CPUs. So also there is the addition of the AOT runtime, which is the executor I mentioned in the previous slide. There is a new format that can be used to export a compile model. When you compile a model, it will at some point generate a C source for the operators that can be then cross-compiled to a given target, as I mentioned. So that model library format is basically a package which will be used by TVM to hold those source files. And this is particularly interesting for microTVM. And there is also now support for AutoTVM. This support, so the auto-tune is now supported on micro targets, and this is quite new. It was a change emerged yesterday, so this is really interesting as well. And the final feature that was added to microTVM is actually a new API, which eases the integration or the addition of new platforms to microTVM. So, and also in another hand, it helps using the added platforms to generate images to a given target of interest. So in that sense, there is a TVM command line interface called TVMC, which is quite nice. So currently, TVMC doesn't support micro target, so it cannot be used to run a model entirely from the command line on a microcontroller, on a micro target. However, with the project API, since it eases the use of the platforms available on microTVM, it's possible to now enable the micro targets, support for micro targets on TVMC. And Linaro has been working on bringing the micro targets to TVMC. So one can use that to run a model entirely from the command line without having to write scripts to do that. And so this is pretty much what the demo is about. So it's about the integration of micro targets to TVMC. And for that demo, I'm going to use that board, which I have on my desk. It has a ARM Cortex. It has a ARM Cortex here, microcontroller, a Cortex M7 running. So the demo consists in running a simple model entirely from the command line using TVMC on that board. So the model itself is quite simple. It just takes a float 32, a single float 32 as input, and will infer a scene of the input value. So it will output a single float 32 value. So I'm gonna go for the demo here using TVMC and running that model on the board I have just shown. I think I need to share my screen. Okay. I hope everybody can see my my video. And so the first thing is you start with a model. For instance, here we have a model exported in a TensorFlow-Lite format. So we have it now. We start with that. And we are going to use TVMC to compile that input model to Cortex M7 board. And we will keep that the compiled operators which are necessary to run that model into a model library format. So after that, yeah, you can see that there is a complaint about the operator not being tuned. This is because we haven't run the auto tuning for that model. So it can be done now that the auto TVM is merged. And now we have a archive here which contain pretty much all the operators, the source code for the C source code for the operators necessary to run that model. So TVMC now, that's what we are proposing, will have subcomments related to a new microcontext where you can create, build, and flash a model. So we are going to use that to create a model, create a project based on the archive, model library format archive generated by the previous compile command. And we specify this is host-driven executor, as I mentioned, and we target, here is the target board on Zephyr platform. So this generated a project which has all the necessary sources and mechanisms to build the model on using the Zephyr RTOS for the Disco board on my desk. So now we have created, we can build the image. We can build the image, specifying the directory. So we are going to build that model and generate a final Zephyr image. And after that, we can flash the model to the device. So once you do that, we are going to be able to run the model using TVMC as well. So to run the model, we have we just specify the folder directory where the model is, and we run it on the device. So this is the value of the scene of available, and you can run multiple times. TVMC, you can see there are random values here. This is because TVMC, since we are not specifying a float 32-bit value, TVMC is generating a random value that is being used in the model. So we can, for instance, use the fill mode and set it to zeros, for instance, and it gives a value for scene of 0. So it infers that value, or you can set input to 1s. And you can see that the real numerical value in that case, this value, so this value here is close to 0, just off by 0.04, and that value of scene of 1 as well is just off by around 0.04. So that was the demo for running the inference model for scene. I have showed in the board entirely from the command line interface. So one doesn't need to write a Python script to do that anymore. Let me store my sharing. Okay, so the commands for the model and the commands I've used are on that slide. If anyone would like to take a closer look, and the idea is to submit very soon that patch to enable microTVM micro targets on TVMC. So we are hoping to have that in the following weeks. So that's pretty much what I would like to share with you. Please reach me out if anybody has any question on that presentation. I would be glad to address it. So thanks a lot. I will stop sharing now. So, yep. Thanks a lot.